Hey, hi. Um, my name's Gerard Phillips. I'm a systems engineer at Arista Networks. I used to work for Stan Advanced Media. Did that for 22 years. So I'm like a broadcast guy, but I speak IP, or I'm an IP guy and I speak broadcast. Depends on how you choose to see that. So what I'd like to talk to you about today is a mixture of network architecture choices, how to build resilience, a few other bits and bobs. So it's an overview of your choices when it comes to building an ST2110 or AS67 2022-6/7 type network. So I'm hoping that this is an interesting topic. I see some spare seats. Come on, everybody else. So what I wanted to cover was a little overview of layer 2 and layer 3. Make sure everyone's kind of up to speed what those things mean. I'm going to talk about designing for resilience and the architectures. And I've got some conclusions at the end. So um, bear with me. If you guys have questions in the middle, feel free to. I'm happy with that. Otherwise, wait till the end. Whatever you work. Let's make this interactive. Um, layer 2. This is kind of like the base layer of networking. It's about the local area. And it's kind of how, I mean, every computer talks to every other computer using a series of hops. It may be just a single hop in a layer 2 environment. If it needs to go to another layer 2 environment, it needs to get routed. So a layer 2 environment is a local environment. It's the smallest failure domain that you can identify in a network. It's really, really widely spread in the audio industry. So we have a lot of layer 2 networks in the audio industry. Dante, Ravenna, for example, typically layer 2 networks. And that's because of a number of things. It's simple, it's scalable, no complexity, probably cheaper, you don't need a router. But it's because the flows are low bit rate. They're a megabit uncompressed for a mono channel, right? Um, you're building an undersubscribed network. You may have a series of megabit flows on a gigabit link. So you can have a lot of those, right? There's no challenges in terms of the amount of bandwidth you're trying to pump across the network. For whatever reasons, a lot of those kind of Dante Ravenna systems, they have layer 2 scoped protocols being used for control. That means they can't actually function outside of that layer 2 network. They're using MDNS or they're using multicast address ranges which are only available locally scoped in the layer 2 network. They cannot be routed, they cannot escape. Okay, so I'm not going to call it legacy because it's an industry that's, adds massive value still. But there's a ton of kit out there, Dante Ravenna type things that feel like they ought to be integratable into our 2110 networks, and they are, but they have given us a view of how to architect an audio network or a media network, which we need to be very careful about. Limiting ourselves to layer 2 is not a great thing to be doing for 2110. Layer 2 isn't going to work for high rate multicast. It isn't going to work if you want to limit the failure domains. It isn't going to work if you want to make sure that those large streams don't cause trouble in your network. Let me give you a very quick example. Here's two switches, layer 2 network. Multicast, so IGMP joins and leaves, okay? But within this sort of system, you have to have a querier, a thing that's in charge of making sure snooping works, which is the mechanism by which multicast is delivered in a layer 2 network. And the way this works is all of the multicast flows from this guy have to be delivered to the querier, okay? So that's okay when it's audio, because there isn't very much of it. But if you're now talking about 2 gigs, 1 gigs, 11 gig flows, they all come across this pipe, okay? These 3 cameras, they all come across here, even though they're not needed. So suddenly, you have to build a network here that is capable of all of that bandwidth, okay? That's not a scalable or sustainable proposition. That's why we end up wanting layer 3. Layer 3 allows us, is this audio working okay? It seems to kind of phase in and out, okay? Layer 3 allows us to treat these two now as routers. And so you have a subnet here maybe, or 2 or 10 subnets, and you have some different ones over here. Layer 3 routing will allow these to happen. Multicast routing will allow this to happen. If I only want the multi-viewer here and the camera and another multi-viewer here, routing will allow me to deliver only the red one here and only the blue one here. So suddenly you're not flooding traffic across the network. Suddenly you're limiting the traffic. You're also limiting your failure domain. If something goes wrong in this switch, and so stuff starts flooding, it only floods in this switch. in the VLAN on this switch, in fact. So you've reduced down what gets broken if something goes wrong. What we need to start thinking about, now that we don't have to build the world's fattest pipe here, is that you may need to control what you flow across that. IGMP will do that for you, but it's not bandwidth away. You may need an SDN system, software-defined networking or flow orchestration system, to choose what flows to go across there. I'm not going to labor this point. The fundamental thing that you need before you can get a multicast routing system is a unicast environment. You need to have IP routing working before multicast routing works. There's tons of different routing protocols. The data center guys use BGP. It's not such a well-used routing protocol in kind of general use, but it's the one that I would recommend. It's very flexible, very resilient, completely standardized, very fast convergence. So let's talk a little bit more about designing for resilience. Because what we're talking about now is 2110 networks where your live production is happening across that network. Why have you gone to 2110? Probably because you're looking either at a very big system, because you have a lot of content, or you're looking at a system to transport valuable content, UHD football or something, right? That's why you've gone IP, because you need the scale that IP can deliver. I don't know, what's the biggest 12 gig SDI router you can buy? Anyone know? You know, right? Is it 256 squared? Yeah, I mean, 256 squared feels right. I don't know the answer, right? But I mean, if you look at building it out of quad SDI, it would be a quarter of the size of an 1152, right? So I'm not seeing a lot of people building 12 gig cross points, right? So I think if you want to get to any sensible scale with UHD, you're going to struggle to achieve that in SDI. I'm not telling you that SDI is dead, and I'm not telling you that you've got to go IP. I'm just saying, think about what you want to get to in terms of end scale. These are the reasons you got 2110, right? I'm blabbling. The point is, you're looking for a resilient network, because this is valuable content. Okay? So there's a lot of ways that you can define resilience. There's a lot of ways you can create resilience. Dash 7, 2022, Dash 7, 2110's version of Dash 7 gives you diverse paths, gives you the ability to have two flows. If one of them stops, or if one of them is being maintained, or you lose a packet on one of them, the other one is still there. So that's kind of fairly fundamental. It's a you have a completely separate network potentially, or you have a logically diverse network. So now we can survive the first failure, right? So we lose a switch, or we lose an endpoint, or we lose a fiber, or we lose an optic, or we need to do some maintenance. The second one is working. Now back to the previous session, what you need is really good monitoring. You need to make sure that both of them were working at some point, so if you happen to lose one of them, you haven't lost the one that was working and the other one wasn't, right? So banging on the monitoring stick. Dash 7 also gives the opportunity to do planned maintenance. You know, you make sure they're both running happily, you take one down, the other one's still running, you do planned maintenance, you bring it back. So you can run a 24/7 operation with IP. You just need to have that resilience and know you have that resilience. What about the second failure, right? Because, you know, maybe you have a failure, maybe you order a spare, maybe you've got a spare. There is now a window where you don't have one of something, right? So there's a bunch of stuff that we can do in the network to mean that the second failure doesn't have to be the last failure you have before you're off air. And there's nothing here that is not stuff that we're doing in the data center every single day of the week. This is the way they maintain their uptime. This is the way they keep their systems running. So you need to make sure you choose quality components. Make sure the switches are reliable. Check the MTBFs. Make sure the operating system is reliable. It's all software, so that's got to be well written. Choose good optics and good fiber. You know, you think about what stuff's got bad MTBF. It's the physical stuff, right? It's the fiber. It's the fans. It's the PSUs. Now, you're kind of covered there because the fans and the PSUs and the supervisors tend to be available as resilient N+1 type things. So that's good. You can lose a ton of fans before you're in trouble. You can often lose a fabric module, which is kind of like the big thing that does the switching between line cards in a switch. They're often resilient N+1. Um, Now we're into stuff that's maybe less obvious. So if I need a 10 gig link between this switch and that switch, you need to put two 10 gig links in, right? And you need to be able to not have one of them operational and still get the workflows you need. If you lose one of them, you need to know that you're not going to oversubscribe, or you're not going to be in trouble because you needed 20 gigs, right? So you don't need to double it. You just need an N+1 on the places where you care. And that typically is between switches, between data centers. We've already got our -7 at the host, so that's covered. Servers are often multi-home, dual home, so that's covered as well. Things like SDN, they can take advantage of these two N+1. They can use that. They can reroute. They can use the resources that are available. So that kind of limits the impact on your workflows if you lose something. Maybe you were using that 2 times 10 gigs. SDN can potentially refactor your workflows such that having lost one of them, you still can do 90% of what you're looking to do. You still got your camera paths and your TX paths, maybe. I wanted to, this is kind of a bit of a noddy example, but here's a little leaf and spine, sending the camera to the multi-viewer. This is the path the traffic is taking. Okay, it's a flow-based system, just keeps doing that, right? If that were to happen, you've lost that one, you want to build a system in which that can quickly flop over. So you don't want that to be a static, always fixed route. You want the system to be able to reconfigure so that that one dies and it chooses a different path. Now that could be a result of inherent things within networking like ECMP, equal cost multipath. It could be a result of the SDN controller understanding a failure's happened and it needs to reroute critical signals. It doesn't really matter how it happens, you just need to make sure you have those capabilities in hand. You probably need to test them when you build your system. So let me talk a little bit about the different architectures available. So 90% of the systems out there in the market working today with customers are pretty big monolithic systems. RTL BCE, there's lots of other ones, Timeline Truck, NEP trucks, plenty of them. So you can see the -7, red and blue. It's very simple. These guys are non-blocking. They're line rate forwarding. They're very simple. IGMP works really well here. There's nothing to orchestrate. These flows go this way and those go that way. You can get to an amazing scale with this stuff as well, right? So depending on where you need to get to, 16,000 square SDI equivalent they're bigger than this, but they're still monolithic switches. Almost 2,500 hosts at 25 gig. That's a lot of endpoints, right? Now the downside is you've got a centralized switch. You've got to be able to get to everywhere from that one switch. So that maybe that makes your optics more expensive. Means you've got a bigger failure domain, certainly. But nothing wrong with it as an architecture if you want simplicity and you know how big you need to get to. Perhaps you use that as a start point, and as you expand, you add some leaves. Now you're building a more blocking system, you need some SDN, but you can now keep adding these leaves as long as you like. And you can start build a much more scalable system with, the endpoint of this is almost undefined. It just depends how big these are, how much bandwidth you want, and how many leaves you stick on. So this is how we're getting to the really, really big systems that are being designed and put in now. Wanted also to cover two things here, really. Leaf and spine, you'll hear that all over the place. This is how the data centers are built. It's a very good scalable architecture for Unicast. You need to be a little bit more careful with multicast. Have a chat with your network guys and work out what the limitations are. It works fine, you just need to understand there are some scale limitations. This is a completely air-gapped red and blue, traditional air-gapped network. So the red stuff can only see the red stuff, the blue stuff can only see the blue stuff. So there's no possibility of losing flows, having the wrong flows, delivering flows to the wrong network, okay? There's guaranteed diversity. Typically layer 3, typically BGP. Orchestration is my personal recommendation is orchestrate this. The failure domain is now much smaller. You lose a switch, you've lost a part of your system. These switches could be in different facilities. They could be in different rooms. They could have different applications. So you've started to build a much more flexible system. It's probably not non-blocking, but then your big system today is probably not non-blocking. It's probably a bunch of SDI routers with tie lines in the middle. That is not a non-blocking architecture. I don't think you need a non-blocking architecture. You could start with a single leaf pair, and then when you get bigger, you add the spines, you add more leaves. So it's very scalable. This is kind of like a hybrid network. This is reminiscent of what CBC Canada is putting in. You have essentially a red network and essentially a blue network. But there are some switches that are sat in both networks, both red and blue, purple, if you like. And that's the advantage of things like single-ended devices, microphones, embryonics, monitors, things you don't care too much about. They can live in this switch or these switches, but they can be available to both networks. So you build a flexible system. Normal network technologies will allow you to make sure nothing bad happens between these two switches. It's mostly air-gapped, so you've got that security, the path diversity, but you can add in these single home devices. So it's kind of a step to this one, which is a purple network. It is both red and blue, okay? So now you've connected, you still have your red and your blue flows, you still have your two flows. You make sure they go into physically separate switches, but the switches aren't identified as red or blue. They can be anything you feel like. Now you really need an SDN controller here. You need to make sure that you don't have the red and the blue flow from this camera both on the same spine, because now you've lost your diversity, you've lost your resilience. You're in trouble if that spine goes down, right? But it's just a software task. It's a logical task. You can make sure that the red and the blue from here always go through two different spines. The benefit of this is if you lose that spine, you can choose how to use the same bandwidth you got left from this spine. Do you want to use it for diversity or do you want to use it for a number of flows? You can make that choice. It's a trade-off. Downside, more complicated SDN required. Something that understands the network and give you logical diversity. This is the only difference here really is I've added some transcoding and I've added some storage, right? So if you have a good SDN system and a purple network, you can start thinking about this as a converged network. You can start thinking about this as your ST2110 protected by the SDN, and you can start running other workloads or other network capabilities on top of that network. You could run VXLAN here, have layer 2 mobility for your transcoding services. You could run your Avid network over the top of your 2110 network. You can start to kind of think about cost savings or the workflow simplicity of having the storage for your playout server in the same network, not having to transfer it across a bottleneck between the networks. It's not for everyone. It is more complex, needs a more complex SDN controller, but it's definitely much more COTS, much more data center. TPC Switzerland is looking like this. So I think I'm running out of time. Just to kind of conclude, there's a ton of architectures. They're all different. They add different things. You can move from one to the other, from monolithic to leaf and spine, or from a pair of switches to a leaf and spine. Think very carefully about whether you're going to need an SDN controller. You can start IGMP and go SDN later. There's not a problem with that at all. Choose cloud scale IP infrastructure. That's going to give you the technological advances that you need. It's going to give you the benefits that the cloud titans are getting: 400 gigs, quality, scalability. I mean, that kind of is almost like one of the big things that I would say about the whole move to IP for broadcast. Try and make it as generic and COTS and cloud as you possibly can. That way you can jump on that train. You'll get all the benefits, you get the cost benefits, you get the speed benefits, you get the reliability benefits. The moment we head back down the rabbit hole of this being bespoke, it's going to be very messy. So I think that's probably it, to be honest. Any questions?
Thank you, Gerard. Any questions? So I have one. How important is it to get all of your IP infrastructure from the same manufacturer? I mean, is the stuff close enough that I can mix and match, or am I going to run into a problem with control, or how is that all that going to work?
It's a great question. So we go back to the concept of COTS. It's about standardized, off-the-shelf kit, right? There's everything that you need to do, you can do with standardized equipment. You can use IGMP, you can use PIM, you can use OSPF or BGP or ISIS or RIP or whatever you want, right? There's nothing that we need in this industry that is not achievable with a standard. So you can mix and match any PIM-capable set of switch vendors. We do that every interop, right? There's typically Cisco, Arista, Mellanox, Artel, Juniper occasionally. So sure, that stuff just works, right? As long as you still need to follow the things that there's still rules about choosing the switches. They still have to be appropriate switches, but as long as they're using standardized technologies, you can mix and match any of them. When you come to SDN, that's an interesting question, because you're now in a world where a broadcast controller has to talk to a network controller, and that network controller has to talk to the network. And maybe you need two network controllers. Maybe you need one to talk to vendor A and one to talk to vendor B. That's still an okay architecture. It just means that somewhere between the broadcast controller and the network infrastructure, you probably need two different network controllers. Now, that's kind of my point about the open config, is that if all of the network controllers were built using open config as the southbound interface, and actually if they're all built using ISO6 as the northbound interface, suddenly you can mix and match your network controllers, you can mix and match your switching. That's the world of standardization. Now, at that point, you guys can choose best of breed. You can choose the vendor of your choice for whatever your reasons may be.
Is there any logic to deliberately picking switches from different vendors because of, worries about software updates or firmware updates and things like that? I've heard of some installations doing that, and I don't know if they've had much success with that route.
I think it's a very cloud model. So pretty much every cloud has dual vendor capability. Very many of them are us and somebody else. And that's built on the standard space, right? Does that work in this industry? So RTL-BC in Luxembourg did exactly that. They had a Juniper, they had an Arista. When they did that, the level of maturity of the ability to use a single network control layer or a single monitoring system was not there. So they had to choose the least common denominator. So they chose SNMP. It works, but it's not great. So I would say we will get there, but not there right now.
Okay. Thank you very much.
Thank you.
Appreciate it.